Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. Okay, in today's lesson, we are going to look at determining the formula of different compounds based on percentages. So there's two types of formula terms that we use generally. Unfortunately, we use them kind of interchangeably, even though they're different. And the two words are empirical formula as well as molecular formula. And so what I'm going to do is I'm going to explain to you the difference between those, because today's lesson is really going to be around an empirical formula. An empirical formula is essentially your smallest whole number ratio of atoms of each element in that compound, and it can be calculated from different types of data, especially mass data. Now, when it comes to ionic compounds, they're already in its empirical formula because they're always in their lowest whole ratio. So for instance, CuO, copper 2 oxide, that is the lowest ratio it can be. It's 1:1. This would never be written as Cu2O2. It doesn't exist as that. The lowest ratio within the crystal lattice is 1:1, and so this doesn't exist. Now, where it does come up is something like molecular compounds such as H2O2. This is hydrogen peroxide, and this is what we would call the molecular formula. The molecular formula is literally how many atoms of each type of element you have in the compound, not necessarily in their lowest ratio. So for instance, the molecular formula for hydrogen peroxide is H2O2 because that's literally what it is. But the empirical formula, I'm just going to call it EF, for H2O2 is actually just HO. That's the lowest ratio. It's 1:1. So today we're really just focusing on the lowest ratio type of questions, which is the empirical formula. In our next lesson, we're going to expand on that and we're going to turn an empirical formula into a molecular formula. So that would be in next lesson. So let's focus on what we're dealing with now, which is, again, empirical formulas. So I'm going to pick another ionic compound here, calcium chloride, CaCl2, and I just want to talk about really what do these subscripts actually represent. Okay, so even though there isn't a 1 underneath the calcium, we understand that this is 1 calcium for every 2 chlorines, in this case chlorides. And so this is really a mole ratio. This is a mole ratio. There is 1 mole of Ca2 plus for every 2 moles of Cl minus, and this is in every 1 mole of CaCl2. Really, these numbers underneath here are a mole ratio. So if I could figure out the number of moles from a percentage, I could then turn that into a mole-to-mole ratio. And so we're going to try a couple questions here first together, starting with some iron oxide compounds. So in this first question, it says, calculate the empirical formula of the compounds with the following percentage composition. So we got 77% iron and we got 23% oxygen. Now, what I do is I just pretend that this is a 100% total, which it is, but I call it a 100-gram sample. So rather than saying that this compound is 77.7% iron, I actually call it 77.7 grams of iron. Because if I call it 100% sample, 100 grams, then 77.7% of 100 is going to give me 77.7 grams. And then the same thing would be true here. This would be 22.3 grams of oxygen. So what I want to do is I want to get a mole-to-mole ratio of iron to oxygen, and then I can come up with the subscripts. So my very first step is really just to convert the grams of iron into moles of iron and the grams of oxygen into moles of oxygen. So let's start with iron first. So we have 77.7 grams of iron, and I want to turn that into moles of iron. Now, what has moles and mass in it is molar mass. So there are 55.85 grams of iron for every 1 mole of iron. Now I'm using unit analysis here, but essentially all I'm doing is using this equation. Moles is equal to mass over molar mass. Now, putting this in my calculator, everything on top, hit divide, everything on the bottom, hit equals. When I punch that in my calculator, I get a value of 1.3912 moles of iron. And I'm not going to round it at this point. And I'm going to do a similar process here for oxygen. So I have 22.3 grams of oxygen. Again, this is just imagining it's a 100-gram sample, and it has 22.3%, which is 22.3 grams. There is 16.00 grams of oxygen in every 1 mole of oxygen. I take everything on top, hit divide, everything on the bottom, and I hit equals. So when I punch that in my calculator, I get 1.39375 moles of oxygen. Now, I can see that these numbers are essentially the same. There's a little bit of a difference here when I get to the thousandth of a mole, which I'm not really concerned with. Now, what I really have here is this formula, Fe 1.39, O 1.39. But that's ridiculous. This mole-to-mole ratio should be whole numbers. Now, how you do that is you simply divide the smallest number by the bigger number, and in this case, they're the exact same numbers. This really is just FeO, because this is a 1-to-1 ratio. So I now know that this is iron to oxide. For the next question, it is very similar, almost an identical setup. The only difference is this 70% is really going to be 70 grams of the sample, and this 30% is going to be 30 grams. So essentially only this number will change. Obviously that's going to give us a different mole ratio coming out in the end. So we are going to have to work through that. So again, starting with iron, I would say that we have 70 grams of iron times for every 1 mole of iron. It weighs 55.85 grams. Again, everything on top in one set of brackets, hit divide, everything on the bottom, grams cancels out with grams, and I'm left with an answer of 1.2533 moles of Fe. Let's do oxygen. So oxygen would now be 30 grams of oxygen, all over 16.00 grams of oxygen for every 1 mole of oxygen. Everything on top in one set of brackets, hit divide. Everything on the bottom in one set of brackets, hit equals. The grams will cancel out, and 30 divided by 16 is 1.875 moles of oxygen. Now, this is a little bit different in that the numbers are not the same, so this is obviously not a 1-to-1 mole ratio. In order to turn what essentially we have here is Fe 1.25, O 1.875 into actual whole numbers, is we take the smaller of the two values, in this case 1.2533, and we divide both of these numbers by that number. So 1.2533 divided by 1.2533 is going to give us a 1. So now it's Fe1. And then I do it below, so 1.2533. And if I put that in my calculator, I get a value of 1.496. I'm going to round this up to 96. I'm going to round this up to 1.5. So now we have Fe1O 1.5. Now this still isn't adequate enough. I want to make these whole numbers. And so essentially all I'm going to be doing is multiplying these subscripts by whole numbers until they turn into a whole number. So for instance, I would first multiply both these numbers by 2 to see if it turns these numbers into whole numbers. So this would turn it into Fe2O3. Those are whole numbers. This is iron 3 oxide. And that is the correct answer. Now, if I multiply by 2 and these still weren't whole, all I would do is then multiply them by 3. And if that didn't make them whole, I'd multiply them by 4, and so on and so forth until I get a ratio of whole numbers as my subscripts on the empirical formula. Our next question is very similar, however it is not an ionic compound. So the question asks, a hydrocarbon, a compound containing only hydrogen and carbon, has the following composition by mass. The hydrogen was 7.69% and the carbon is 92.31%. Calculate its empirical formula, not its molecular formula. So again, what I'm going to do is I'm going to assume these percentages add up to 100%, which they do, and I'm going to call it a 100-gram sample. And so this would then become 7.69 grams, and this would become 92.31 grams. Remember, I'm able to do this because we're simply coming up with a ratio, and so I could choose really any sample size. I could even say it's a 1-gram sample, but then I would have to adjust these numbers to being something like 0.0769 grams and 0.9231 grams. So it's just arbitrary. So let's start with our hydrogen. I would start with 7.69 grams of hydrogen, and I need to turn that into moles of hydrogen. Now, for every 1 mole of hydrogen, it weighs 1.01 grams. So, in brackets, everything on top, hit divide, everything on the bottom, hit equals, grams of hydrogen cancels out with grams of hydrogen, and I'm left with a value of 7.6138 moles of hydrogen. I then have to repeat that step for carbon. So carbon would be 92.31 grams of carbon. I need to turn that into moles of carbon. So for every 1 mole of carbon, it weighs 12.01 grams of carbon. The grams of carbon cancel out, everything on top in one set of brackets, hit divide, everything on the bottom, and hit equals. And when I punch that in my calculator, I get a value of 7.686 moles of carbon. Now looking at these two values, they are so close together, I can see that this is a 1-to-1 ratio. Being off by roughly 6 to 7 100ths of a mole is just a part of error when we actually calculate these percentages. So if I divide by the smallest number, and I'm just going to use this one because it is slightly smaller, I get a value of 1 for hydrogen. And then I divide here by that number again. I get a value of 1.0094, which I just assume to be 1 as well. And so the empirical formula would be 1 carbon for every 1 hydrogen. So again, there is no such compound as just CH. There is C2H2, that's ethine, and this could even be something like C6H6, which is benzene, which is a very common hydrocarbon. But they haven't given me enough information yet in order to figure out what whole compound it would be, and that is something we're going to look at in our next lesson. In our next question, we aren't doing the same thing as we did in our first 2 questions. We're actually doing the complete opposite. So for questions 1 and 2, we were taking a percentage and we were turning them into a mole ratio, which was then our mole ratio of our chemical formula. here we are actually starting with a mole ratio, and we're working towards a mass, which is going to be used to get a percentage. So two things before we even start talking about the question itself is I want to pull out two concepts. First of all, when I have CHCl3, I have a mole ratio, which is the following. For every 1 mole of this compound, CHCl3, I have 1 mole of carbon. That's a subscript on carbon. I have 1 mole of hydrogen. That's a subscript on hydrogen. And I have 1 mole of Cl. 3 moles of Cl. So that's the first thing I can take away from this question without really reading anything. The second part is this percent composition by mass. So whenever you're doing a percentage, you usually have a part over the whole. So if this is a mass percent, I need grams of something over grams of the whole. So and then multiply by 100%. So the mass of the whole is the mass of CH3Cl3. What goes on top is going to change 3 different times. In order to figure out my percentage of carbon, this is going to have to be carbon once to get the percentage. Then I'm going to have to do it again to solve for hydrogen and putting hydrogen on top. And then I'm going to have to do it a third time to get the percentage of Cl to put that on top. So we are going to need to be able to turn these moles into masses so we can divide them in order to get a percentage. So I'm just going to start with carbon because it's the first thing in the compound. So I am always referencing my main compound because I want to get the ratio in mass of my part, in this case carbon, to my whole, which is CHCl3. So I'm going to start with that mole ratio. For every 1 mole of carbon, I would have 1 mole of CHCl3, or you can say it the other way. For every CHCl3, I have 1 carbon in it. Now what I want to do is I want to turn these into masses. My goal is to get the mass of the part, in this case carbon, above the mass of the whole, which is the CHCl3. So I want grams of carbon on top, and I want to get grams of CHCl3 on bottom, and I want to get rid of these moles of carbon and moles of this compound CHCl3. Well, what has mass and moles in it? Molar mass. So for every 12.01 grams of carbon, I have 1 mole of carbon. And so what I've done is I've converted the moles of carbon into grams of carbon in this first step. So currently I have grams over moles. What I want to get is to get rid of this moles of CHCl3. So I'm going to put that on top of the next fraction. For every 1 mole of CHCl3, and I would have to calculate its molar mass, which is 119.37. And so now I have the moles of CHCl3 canceling out with moles of CHCl3. So if we follow the units right now, I have grams of the part above grams of the whole, and the only thing left to do would then be to multiply this by 100%. So let's do that. Let's take everything on top, divide it by everything on the bottom, hit equals, and then we're going to multiply that by 100%. So when I put that in my calculator, I get 0.1006, but then times 100% would give me 10.06% carbon. So what I would like you to do at this time is pause the video and try to figure out the percentage for hydrogen and chlorine. So now that you've had a chance to do those questions, let's go through them together. So starting with H, I have the same mole to mole ratio. So 1 mole of hydrogen for every 1 mole of CHCl3. I do need to set up two fractions to do the two conversions. So there is 1.01 grams of hydrogen for every 1 mole of hydrogen. This will cancel out the moles of hydrogen and turn it into grams of hydrogen. And then for every 1 mole of CHCl3, it weighs 119.37 grams of CHCl3. This will cancel out the moles on the CHCl3. I take everything on top, hit divide, everything on the bottom, and hit equals. This gives me an answer of 0.00846. Multiplying that by 100%, I get simply 0.84. I'm going to round it up to 5% of hydrogen. We have one last one to do for chlorine. In this case, we do actually have not a 1-to-1 ratio, but a 3-to-1 ratio. So for Cl, I would have 3 moles of Cl in every 1 mole of CHCl3. Again, I have to get rid of the Cl. So this would be for every 1 mole of Cl, it weighs 35.45 grams of Cl. This will cancel out the moles of Cl. I then need to convert over to grams of my CHCl3. So for every 1 mole of CHCl3, I have 119.37 grams of CHCl3. This will cancel out the grams. This will cancel out the moles and convert it to grams. Everything on top in one set of brackets, hit divide. Everything on the bottom, hit equals. And I get a value of 0.8909, but I have to multiply that by 100%, which will give me a total of 89.09%. Now, if I add all of these percentages up, it's going to get me very close to 100%. Please understand there is going to be a little bit of error with the rounding, but I should be able to get very, very close to a total of 100%. In our last question, we are going to look at just a larger compound with a slight twist to the question. So it talks about PAN and it being a component of smog, and it says that it contains carbon, hydrogen, nitrogen, and oxygen, and to determine the empirical formula. So again, all we're trying to do in this question is we're trying to figure out the subscript or the number of moles in the ratio of carbon to hydrogen, oxygen, and nitrogen in whole numbers. But when I continue on in the question, what I notice is they give me the percentage of carbon, they've given me the percentage of hydrogen, and they've given me the percentage of nitrogen, but they haven't given us the percentage of oxygen. So what I'm going to do is I'm going to say 100% is the whole compound, and I'm going to subtract away these other percentages to figure out what's left over. So if I go 19.8% minus a 2.50% minus another 11.6%, I'm going to end up with a total of 66.1% left over, and that would be oxygen's percentage. Of course, I'm going to turn these all into grams, 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 and grams in my calculations. So I'm going to set up all the work first, starting with carbon. I would start with the 19.8, but I'm turning the percentage into grams of a total sample of 100 grams. And I want to get that into moles of carbon. So for every 1 mole of carbon, it weighs 12.01 grams. Then I move on to hydrogen, which is 2.50 grams of the total compound. For every 1 mole of hydrogen, I have 1.01 grams of hydrogen. And we're just going to keep going through. So with nitrogen, it would be 11.6 grams of the sample multiplied by for every 1 mole of nitrogen, I have 14.01 grams of nitrogen. And then lastly, oxygen would be 66.1 grams of oxygen. And of course, that would be for every 1 mole of oxygen, I have 16.00 grams of oxygen. So starting at the top, grams cancels out with grams, and if I put that in my calculator, it would come out to 6486 moles of carbon. Keep going down, hydrogen would work out to 2.475 moles of hydrogen. Nitrogen comes out to 0.8279 moles of nitrogen. And the last one would be 4.1312 moles of oxygen. So I have all these numbers. In order to get them into whole numbers, I'm going to first have to start out by dividing all these numbers of moles by the lowest amount of moles. So the lowest amount is the number of a nitrogen here. So I've got 0.8279. I'm going to divide this by 0.8279 and so on and so forth. Okay. So plugging these into my calculator, I get carbon is 1.99 moles. I'm going to assume that's close enough to 2. Hydrogen comes out to 2.989 moles. Again, I think that's close enough. We can call that 3. With nitrogen, that's going to come out exactly to 1. And with oxygen, it comes out to 4.989, which again, I think is close enough to 5. So when I write this as an empirical formula, it would be C2H3NO5. Now this could also be the molecular formula, or it could be a multiple of these subscripts. So it could be C4H6N2O10 or any other multiple of those subscripts. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.